We just created a naive algorithm to compute GCD. The idea was very simple. Start with the smaller of the two numbers and then start going downwards. Wherever you find a number that divides both the numbers, that has to be the GCD. So very simple idea. But then let's think about what happens with the runtime here, right? Now notice that this algorithm is going to run at most, okay, at most min of A and B times. And this will happen when the numbers in fact are co-prime, which means the GCD is actually 1, because anywhere else there's a break statement that will take care of the fact that, look, we found a factor and hence we found the GCD, right? So the worst case scenario here is when we have, let's say, GCD being the numbers being co-prime, and the running time will scale, or the number of operations, let's say, will scale with the minimum of A and B, right? So it's the minimum that matters. The maximum really doesn't matter, right? So I can put a very large number, or I can put a, let's say, a not so large number, so long as it's bigger than the, let's say, the first number. So the minimum of the two counts, and this is important, right? So let us analyze this, let us get some data from this, like we were doing earlier, by actually running it for some numbers A and B, so that we can then start looking at what's going on. So I get back here to my code. I just, let's say, once again, go and, so I can just go and say import time. In fact, probably I don't need to do this because I've already done this earlier, but never mind. I can just go and say t naught is equal to time dot time. I we'll come back to this later. T1 is equal to time dot time, let's say, once again, so snapshot of time before and after. That tells me how long the algorithm took to run. So I can just go and print, let's say, t1 minus t0. Now for the purpose of this, let's say, demonstration, I'm just picking up two numbers just to sort of make a point. There's nothing special about these numbers. I just kind of pick them up. So I'm going to say the first number, I'm going to put the first number is, let's say, in first. So 8500000110. Now just a random number chosen, but rather large, right? So this is like whatever, it's got 1 2 3, so this is like 1 2 3 4 5 6 7 8 9 10. Yeah, however, remember the running time depends on the smaller of the two numbers. So I'm going to start with, say, a number here which is 1002301. So the running time is dominated rather by the running time is a function of the smaller of the two, which means this number. When I run this, right? So when I run this, it turns out, okay, so I should also print the GCD, so that, let's just say G is the GCD here. So I'm going to print, say, G and T1 minus T0, right? So now when I run this, you notice that the GCD is 1, which means the algorithm indeed ran for this many times, and it took, well, let's say 0.1 second to do this. So 0.09 seconds to do this. Not bad. Let's run it a few more times maybe. So this time a little bit, so 0.0 something, right? Now I am going to just add a 0 to this. The intent, oh sorry, I'm just going to add a 0 at the end. Now intention here is to increase the smaller of the two numbers, increase the smaller number. However, notice that clearly these two are no longer co-prime, but it turns out that this is okay, because when I run this, I find that the GCD is 10, which means that, look, even though this GCD is 10, but 10 is very small compared to this, so it really ran approximately for this many times, which is perfectly fine, right? Now let me just keep increasing this. Let's say I add one more 0 here. You notice that the running time increases. In fact, it's already gone into something like maybe, last time when I ran it was smaller. It's already, say, roughly 10 seconds, so almost 9.9 seconds, right? If I were to add, say, one more 0 to this, I clearly expect this to increase even further. In fact, this is going to take a long time, right? Because that took, let's say, around 9 seconds. I'm expecting this to take approximately 90 seconds. And really the reason for this is not at all difficult, because the GCD for these two numbers is still 10. And hence I'm running the loop approximately this many times, right? And this is like a large number, really testing for every number if the divisibility condition is true or not true, and this condition is being run for every number, this as well as this, and is being done. So a lot of operation is being is kind of happening here, which we'll realize later on is not necessary. Remember, the question to ask always is my algorithm doing more work than what it should be doing? In this case, it is indeed doing more work. I have taken these two numbers, quite large numbers. The complexity depends on the smaller of the two, which is this. And this itself is quite large, right? We will see with the efficient GCD algorithm, you will run this in a much, much, much faster time, telling you conclusively that this algorithm was indeed quite inefficient. So it did get over finally, and it's 96 seconds as we had predicted. You know, again, the point is 10 times more the number, the 10 times more approximately the runtime, right? So again, these numbers are not exact, these numbers are not extremely precise, but the trend is unmistakable. In fact, when I had run it earlier, for some reason, these had run faster. This is okay. Like I said, the exact numbers could differ when you run it, could be different. But what is unmistakable here is that, look, when I go from here to here, the number of operations increased by approximately 10 because the GCD is 10 still, but this number has increased. The smaller one has increased by factor of 10. So there's approximately a factor of 10 increase in the number of computations. Again, a linear scale is going on, just like our naive prime number finding algorithm. And indeed, it took 10 times as much time. Went from approximately 9.6 seconds in our present run to say about 95 seconds or 96 seconds, right? Clearly, a linear scaling is visible over here, right? We will come back and see how we can make this smart. And in fact, the same computation, which is taking so long now, will take a lot lesser time. And we'll see why that happens. Once again, I hope you found this interesting. If you want to understand algorithms in a simple, lively manner, look at the Ybyte algorithms on Olympia track, www.ybyte.in, and enjoy programming. Take care. Thank you so much. Bye bye.